In the last video, we looked at covalent bonds, which is the sharing of a pair of electrons between two nonmetals. But those electrons are not always equally shared. Some nonmetals tend to have a stronger attraction to electrons than others. And that's where we get the distinction between polar and nonpolar covalent bonds. So this represents an electron cloud of electrons being shared between a hydrogen and a fluorine. And when you look at this shape, you see that there's a much bigger region of space around the fluorine nucleus because fluorine has a much higher electronegativity, tendency to attract electrons, than a hydrogen nucleus does. And so you're going to get a much stronger attraction to electrons towards fluorine. And so the symbols that you see are lowercase deltas. And so what we get in a unequal sharing of electrons is that you get part of this molecule is partially charged. And it's not like with an ionic compound where you had a complete transfer of electrons, you had a positive and a negative ion. We have a molecule, and so the hydrogen and the fluorine are connected together through a shared pair of electrons. That shared pair of electrons spends way more time on the fluorine side than the hydrogen side. So those delta positive and delta negatives are partial charges, so they're not a complete charge. And when we have this unequal sharing of electrons, we have what's called a polar covalent bond. In a polar covalent bond, you have poles, just like the Earth has a north and a south pole. A polar bond has a positive and a negative site to the molecule. One side will be positive, the side that's less electronegative. One side will be partially negative, which is the side that is more electronegative. With respect to polar bonds, the only truly nonpolar bond are those between atoms of the same element. So think back to our last video on the diatomic elements. If you got a nitrogen bonded to a nitrogen, you're going to have an exactly equal sharing of electrons. That said, any other combination of nonmetals, you're going to have particular degrees of polarity, which is going to be determined by an electronegativity difference. The greater that electronegativity difference, the more polar your bond is going to be. So the more polar molecule is, the more it behaves like an ionic compound. And one of the ways that you can think about this is with solubility. The rules of solubility are like dissolves like. Things that are charged, things that are either ionic or polar, tend to mix together. Things that are not charged, typically nonpolars, do not mix. So think about carbon-hydrogen bond, for instance. So the electronegativity of carbon is 2.6. The electronegativity of hydrogen is 2.2. If you subtract those two, you get an electronegativity difference of 0.4. And generally, we consider 0.4 or less to be nonpolar. And if you look at the slide here, it says nonpolar-ish because, again, any difference in electronegativity, and you get slight polarity. But here's the deal. Carbon and hydrogen is the major constituent of fats and oils. And fats and oils don't do a very good job dissolving in water. They are primarily nonpolar. So that's why, even though, unless the difference is zero, there's going to be a slight unequal sharing. But anything 0.4 and less is not quite enough. And so our general scale for polarity is going to be things 0 to 0.4. That includes 0.4. Because that's the carbon-hydrogen bond, are generally considered nonpolar. If we're in the range of 0.4 to 2.0, we consider those things to be polar covalent. And if your electronegativities are greater than 2.0, then you have an ionic compound. But of course, we really don't need electronegativities for ionic compounds because we're going to identify those by looking at metals and nonmetals. So here's a nice image that kind of breaks all of this down. So if you have a nonpolar covalent bond, think about the Cl2 here. You're going to have an electronegativity difference of 0, and you're going to get a complete equal sharing of electrons. So the electron clouds on either side of those nuclei are mostly equivalent. If you have between 0.4 and 2.0, you're going to get an unequal sharing. So you're going to have a bigger electronegativity or a bigger electron cloud around the more electronegative element. And if we have an electronegativity greater than 2.0, It's not going to be a sharing of electrons. One of the elements is going to be so electronegative, it's just going to take the electron away from the other element. You're going to end up with an anion and a cation, and you're going to get an ionic bond. So let's see if you can practice this. So what we want to do is determine the electronegativity difference of the following chemical bonds and identify the type of bond. So I'm going to put a couple of bonds here. You need to grab your periodic table. You need to find your electronegativities, which, if you're not sure where to find them, you should look at the key on your periodic table, and it's going to tell you what number in that square is the electronegativity. Here's a series of chemical bonds. So what I want you to do is go through and see if you can sort out what the electronegativity difference is between these bonds and whether or not they are polar or nonpolar. Pause the video, see if you can sort this out. Okay, hopefully you took some time to do that. If you didn't, pause the video and do it. You really need to practice this, make sure you can find this information. If we want to look at the electronegativities of these elements, and you didn't necessarily have to write this down. If you just subtracted them, that'll be in the next column here in a second. These are the electronegativities of each of these elements as listed. If we do our math here and get the difference, and we're going to take these as an absolute value, so we're not going to worry about positives and negatives here. Those are the differences as they're laid out. Again, differences 0 to 0.4 are nonpolar covalent. Things between 0.4 and 2.0 are polar covalent. And anything greater than that, so take a look at your magnesium oxide there, is going to be ionic. And so if we look at those, you can kind of see how all those bond identifications measure out compared on those electronegativity differences. And I want you to pay close attention down there at the bottom, beryllium and chlorine. The most common compound between beryllium and chlorine is beryllium chloride, BeCl2. So there's actually two BeCl bonds. Their electronegativity difference is 1.6, so we call that polar. But we got a little bit of an issue here in sorting this out, and that's because beryllium is a metal. And so if beryllium is a metal and chlorine is a non-metal, then we should have ourselves an ionic compound here. One of the ways we can kind of test whether or not we think this bond is ionic or covalent is we can look at melting points. And so if we throw those melting points out there, now you can't have the melting point of a particular bond. So for instance, the melting point on the PCl is for a compound called PCl3. And so polar molecules tend to have higher melting points than nonpolar molecules, which tend to have lower melting points than ionic compounds. And when you look at the list of what we have going on here, your two nonpolars, look at those melting points, super, super low, negative 100 plus or 100 minus, depending on which way you're looking at that. Those are pretty big negative numbers. And so you would expect that from nonpolar molecules. When we go and we look at the 1.1 electronegativity difference on silicon and bromine, again, that's a silicon-bromine bond in a compound that has 4 other hydrogens. So we would get into that later. So this is not necessarily directly the bond, but a simple molecule that contains this bond. It's a nonpolar bond, but it's a slightly bigger molecule than the two that I measured for the CH bond and the NO bond. And you get a negative 94 degree melting point. You go up and look at the PCl and you get negative 93. Those are both polar bonds. And so when we look at that BCl2, we notice that that bond is a little, or that melting point's a little bit bigger at 399. But that's less than a good number of ionic compounds. And certainly less than the magnesium and oxygen compound where the melting point is 2000 degrees Celsius. And so for the most part, people consider the beryllium chloride bond to be polar. We can just follow the electronegativity differences, and really pretty much any other compound that you can think of that contains a metal and a non-metal is going to be ionic, and you don't even really need to check the electronegativity differences.